All right. Welcome to the third workshop session. Can you confirm that you're seeing my kind of full screen slide here? Free? Awesome. Thanks. Thank you so much for joining us. We have had a couple of really great sessions so far. I did fail to do a recap last time, but our first session, we kind of went over the general science behind EMIT and kind of some basics of the data structure. The recording for that is now available on the EMIT website, and we can put a link for that in the chat. I also provided it in the email that probably many of you got yesterday as a reminder for this session. The recording for last week still has not been approved, but if we're at the same kind of cadence, then hopefully early next week we'll be getting that one posted, and then the following week we'll post this one as well. We're looking forward to kind of continuing on from where we left off last week to kind of think about a little bit more advanced manipulation of data, and then also thinking about kind of data quality masks and just some things to consider as you're starting to work with and reproject and resample these data. And as with last week, we're going to do a series of two breakout rooms. So in the top right-hand corner where it says participants, you can see all the people who are currently in the main meeting, but then also to the right, there's the breakout sessions. You're able to join those, and then if you need some technical help, folks from the LP DAAC will be there to assist you with getting onto the cloud instance or other technical issues you might be having. And then when you're done, you want to come back to the main session, you can just hit this leave. You want to leave the breakout session, but don't hit leave the meeting, or else you'll have to log back in, which is not the end of the world. And the other thing is, if you do go to those breakout sessions, the main meeting room is still being recorded, so you will be able to go back and review that information so that you don't have to be concerned about missing anything there. All right, I will stop sharing my screen so we can get on to the interesting content here today. Anything else at this stage, or we get ready to get going?
I think we're good. You get going. So I'm going to paste a link in the chat. Bree's already posted this several times, but that's our link to launch the cloud instance. And so when you do that, you should get a screen sort of like this, where you've got your Jupyter Lab instance, and then you can see here in your Explorer that you're in the EMIT data resources folder. Just to check real quick, is everybody getting on pretty quickly? If they've clicked the link, or are there a couple people still waiting? Sometimes it takes a little bit for the servers to spin up.
A bunch of thumbs up there.
All right, great. So the first thing we're going to talk about today is transforming one of the netCDF files that you can download from Earth Data Search into an ENVI file. And so there is a Python library that's hosted in the normal EMIT repository. And then I've made a notebook that basically allows us to walk through how to use it. So if you go into this how-tos folder here, the first thing we're going to do is this how to convert to ENVI. So if you double click that and open the notebook, that'll bring that up. Just to sort of review the controls for the instance here, like up here on the top bar, like the play button will basically execute a cell and move on to the next one. The stop will interrupt it, and the double play button will basically run everything in the notebook. If you should have some sort of issue and your instance crashes or stops responding, you get some sort of error. There are like limited resources on here, and since we've got a bunch of participants, that could potentially cause an issue. If that does happen, you can go to the kernel menu up here at the top and then shut down all kernels. And then you just click shut down all. And what that'll do is that'll close everything that's running in the background. And then when you run a cell, it'll prompt you to select a kernel. I think by default, everyone will just have the one. I've got like two, but you would just want to use this Python 3. So I guess we can get started. This is basically going to convert a netcdf file to ENVI format. And you can open these files in ENVI, newer versions of ENVI, but you'll have to specify like the metadata associated with the file, like the projection and the bands. You'd have to do all that manually. And what this script does is allow you to just open the file. And so like the first thing we're going to do, all of these cells that we run here, you can actually do in command line. Basically, the first thing we're going to do here is we're going to clone the repository from the EMIT utils repository. And so that's going to copy that over to a location here in this folder, or in the EMIT data resources folder. And then after we get that completed, we'll do like a pip install to install that library. This is taking a little longer than usual.
As it's working, maybe you could introduce yourself a little bit more.
Oh, I guess, yeah, I'm Eric Bolch. I'm from the LP DAAC, and we distribute the EMIT data set. And you can get that data from the Earth Data Search website. Just this link right here that I posted in the chat.
While we're waiting, I can ask a question from the Mentimeter here. Somebody says they don't see a license header on the .py files for EMIT utils. Are they released in GPL3 or what license?
That I'm not sure about. I think maybe Phil could better answer that question.
I am not actually entirely sure what our licensing is. I believe it's yeah, I'm gonna have to look that up. I will work on doing that while we're going here and get back to you.
Great, thanks.
Oh, I'm sorry, in the .py files. My apologies. I thought the question was about the .header files. The .py files are released under an Apache 2 license. Most of the repositories, I believe, have a license for the entire repository. In most cases, I think I've gone through and I've added those to the .py files, but in some cases I might have missed them. So apologies there, but it is the entire repository should be licensed under Apache 2.
Great, and then a question, another question, how many GitHub repos are there for these tutorials? I see the github.com/emitSDS and then github.com/NASA/emit data resources. Are there others also?
So those are the two primary ones. I don't think there are actually any others. There are some other data sets or scripts on the EMIT SDS repository, but sort of all the resources for this workshop outside of this one tool are here in the NASA/EMIT data resources repository.
I might add on the EMIT data resources repository. The intent with that repository is that it's going to be kind of the main source for tutorials and scripts and kind of community involvement with these data. So at the end of today, we'll kind of talk about how you may contribute to the repository. And so stay tuned for that.
Yeah, thanks, Aaron. All right, so it looks like that finished running. So now we'll do a pip install, which will make the scripts in that available to run. And so sort of after we've done that, basically like sort of the next step here is to use this script, you have to have an output directory. So like the next step we'll do after this finishes running, it does not usually take this long. I'm curious if maybe there's something going on with the servers we've got set up. But anyway.
I have a question.
Sure.
I've not used this kind of environment before, and I'm very unfamiliar with this layout. Could you just briefly explain like what we're seeing in like the Jupyter Lab and where the resources like are and what we're in right now?
Yeah, so the Jupyter Lab or this Jupyter Hub is basically a Python environment where you can run Jupyter notebooks that's hosted in the cloud. So like when you click that link that we provided, that launched an instance specifically for you that you could log in with your GitHub information. And then now we've got these series of notebooks that we can work through. Specifically this right here, this isn't exactly working within like a Jupyter notebook. Like these are things you could do like in command line to execute this script. We just put it into a Jupyter notebook so it could have the set of instructions with it and it would be easier for people to walk through. So since that's installed, we can create our directory here. We're just making an extra ENVI folder within our data folder. And then what we can do is we can execute this script. And so we'll call Python, and then we select what script we want to run, which is this reformat.py that's contained within the EMIT utilities repository that we downloaded and installed. And then next we'll pick our target granule that we want to convert. And that's in this shared location right here. And then we'll provide where we want to save our output, which is in this ENVI folder. And then this script also supports orthorectification. So if you want to orthorectify it, you can use 2 hyphens to add this parameter, and it'll do that. So we can go ahead and run that. And that might take a little bit of time, but that'll create these ENVI files for you and the header. So you can just open it straight in ENVI without any difficulty.
Okay, so how do we run all of this?
So if you wanted to run this locally, what you could do is you could run these same functions here from command line on your local machine. You would first just want to clone the EMIT data resources repository. And then you could either execute these through the notebook or you could do it just from the command line. And so that'll put that in this data folder here. It's done writing. And do we have any other questions while we're sort of waiting here?
Yeah, there seems to be some questions around the ENVI format that this is converting to. I think that you may have answered some of them, but some of them are that about the header and the .header and .dat file, and so are you creating both of those in this process?
Yeah, both of those are being created here in this process. And actually, I can just go ahead and so you guys.
And I will just step in and comment that normally it does not take this long. This is an issue with how the server is currently running. This is normally a very fast command to execute. So if you're doing this locally, think less than 10 seconds to run that command tops.
Yeah, that's a good point. And if you wanted to open this, you can download it from the cloud instance that we're on if you wanted to run that on there. Or like I said, you could execute this locally, but you could just open it and it also generates the header file. And then you would have something like this in ENVI. It's still running.
Okay, there's another question here in the Mentimeter. Will I have access to these notebooks later? Sorry if it's been answered before. The answer is that yes, they're in the GitHub, but perhaps you can elaborate.
Yeah, so these notebooks, they'll be available in this NASA EMIT data resources repository. We have a separate branch for the workshop that we're going to keep that as is, and then we'll continue to update the main branch. So that'll be available in addition to what we're presenting today. And then also this cloud space will be available, which usually does perform better if you want to use it to do some testing or exploring any of this stuff that we've provided here for the workshop. How is the performance for everyone else? Is it also going very slow, or is it just for me?
I can't even open the GitHub, it just fails. Something's going on out there. I know the GitHub, the website, the link you provided to the lab, to the environment.
Okay.
Yeah, there's in the chat, people are saying it was fine at first and now it's slow. Finals were generated now. Someone just clicked through before you started and it just completed step 4.
Okay.
And Monica, if you're having additional issues kind of beyond that, you might want to kind of virtually walk into the technical help session and see if Aaron can help you more specifically.
Thank you.
Eric, I might suggest that as this is it's a live demo, this is one of the challenges with live demos. So thanks everyone for bearing with us with a joint compute environment. Eric, I might suggest that maybe you move to the next section of the tutorial and we just do it maybe without the executions.
Yeah, we can do that. I'll go ahead and start the next one. I am going to stop this though. So the next sort of tutorial that I wanted to go over is doing a point extraction. And so this is something you would do like if you want to do some sort of classification maybe, and you have some ground reference points in a CSV file and some categories or other information. You can just extract those specific points from the EMIT data set into a separate CSV file. And so here I'll kind of walk through how we would do that. And so like the first thing we would want to do here, again, is just import the Python libraries. To do this, we're going to utilize both pandas and xarray. And sort of the reason we're going to do that is everybody's very familiar with pandas and sort of working with data from there, especially like CSV files. And then for this example, we'll use xarray for the EMIT data set because of some of the features that allow you to do things like this pretty easily. And so we can set our file path, which is this shared location here. And then we're going to use this EMIT xarray function to basically read in the EMIT data set into an EMIT xarray. And this function is included in the modules folder of the repository. And basically what it does is it reads in the different pieces of the netcdf and places them in an xarray data set in a format that allows additional tools like rasterio to be used on the data set. And this function also allows you to go ahead and apply the ortho rectification. And it does that by default. Inside that module, there's also some other sort of useful functions for working with the EMIT data. You can apply the ortho rectification to, I think you should be able to apply it to any sort of data set that's in this format here. And so we can look at this and we can see the latitude and longitude dimensions of the data set and the bands. And then also we've got these wavelengths, the full width, half maximum, and then the spatial reference information. Right here, there's just a 0 value, but that's sort of just a placeholder for the rest of this information that's contained within the attributes. And then here we can see, like we've got our reflectance. That's surface reflectance, that's a long name. Also, this function does pull in all the other attributes. So you've got all your attributes and metadata from the EMIT netcdf file. So next, what we could do, we could just read in our points by reading them from the CSV file. And that file is included here in the repository. It's just this sample coordinates CSV that's in the data folder. There's just 5 points in here. And these are arbitrary categories just to sort of represent that you could have that and carry that information through with this process. Since we've got the EMIT data set into xarray in the format we want, we can just select a single band and plot that so we can spatially visualize where these points are. And then on top of that, we can do like a scatter plot from the data frame object that we opened with pandas. And then we can add some labels to that. So here we can see just sort of where these points are to give us a little better understanding of the information we're going to extract. So the next step we want to do here is we want to set the data frame index By default, it's just sort of an index along the side, but we can set that to our ID number that we have. And so if we do that, we can convert that straight to an X array, and that'll preserve that as our dimension that we want to index on. So after we do that, we can use this select tool, which is part of X array, and you can just specify the latitude and longitude coordinates here using a nearest method, and it'll select and extract those from the X-array data set, and then in just one line, we can go ahead and change that back to a data frame. And so what we'll end up with is like a long form table where we've got our ID, which was our index, and then for each one, we've got all of our bands, all 285 bands, and the reflectance for each band, the lat long, the wavelengths, and the full width half max. You will notice that the category is not here. That didn't carry over. So what you want to do is you can just go ahead and join that category from your points data frame on this new one using the ID. So we can just sort of add that in. And then so here, basically, you've got your 5 points of interest, and we've extracted our reflectance. It's like a good point, like if you want to save this data, you can just write it straight out to be a CSV. And then also we can plot that. And before we plot it, I'm gonna go ahead and remove, or I'm not gonna remove, excuse me. I'm gonna set these values that are assigned to -0.01 to not a number. And those values are basically deep water absorption regions where there's too much noise to discern a good reflectance value. And so we can just sort of mask those out and then plot our reflectance here. And you can easily see which point each one of these is. It looks like I've got a couple questions.
Yeah, there's one. Why did you choose to use ref stereo and X-array separately instead of Rio X-array?
So here, I don't think I actually used ref stereo here, but like I will use it to do the area extraction, just to do a clip, and that is something I think you could also do with Rio X-array. But I don't think Rio X-array supports some of the stuff we're working through here in that CDF format. I'm not 100% sure on that, but I did look at it, and it seemed like this was like a little bit better approach.
Great.
Did we have any other questions?
That was all that I have in the Mentimeter, yeah. Oh, and then one, could you show the CSV output of the points?
Yeah. Let's see how it'll show in this instance. Oh, I don't actually have it here. I can still show that though. Just 1 second. So just opening that with like Excel would look something like this. You would have you would have an ID column, a band column, reflect and slat one, full width, half max, all the columns here, sort of in like a long form, organized by the ID. Does that sort of answer the question on that?
Yep, that's great. Thank you.
Yeah. Well, I guess if that's it, I can move on to the next tutorial.
Yeah, I think that's great. I'm just going to do a reminder. If people can try to use the Mentimeter for questions, the chat goes very quickly and people send private messages, then so your questions can kind of easily get lost. So I just put the web link in there. So if you, it'll be easier for me to do that to get your questions answered. So thanks.
Hey, Eric, before you go away from this plot, could you just, I'm confused about the gaps that we're seeing in like the wavelengths. Can you re-explain that quickly?
Sure. Yeah, so the gaps here, they're basically where the absorption within those regions of the spectrum will be very high. Not a whole lot of light will get through. And that's where water is absorbing a lot of the radiation. And so EMIT basically reassigns those values to this negative 0.01 to take them out. And so when you visualize that on a plot, they just kind of drop off and they have like a line at the bottom. So I just reassign those values to not a number. For the visualization of plotting this, it looks like a little bit cleaner.
Thanks a lot.
Great, thank you. And then we do have another question, which is, can you use these data without ENVI or convert them using any other library than Python functions from ENVI? And I think actually last week we talked a lot about other ways of using these data. You don't have to use ENVI at all. And the recording from last week, if you weren't able to attend, will be posted hopefully early next week, and we'll announce that on the Slack channel, as well as we'll do a wrap-up email once they all get posted. But any other comments on that, Eric?
No, that's it. And for people that are following along, it seems like maybe there's still some issue with our cloud instance that we're working from. And it's not handling this very well today. So that's why I didn't actually run any of these. I'm just kind of walking through it for now. Like maybe at the end, that issue will be resolved. We can take some more questions and try to go through something again. If anybody would like.
I do have a slight update on that front with how things are running. It sometimes accidentally, even though we consciously know that we should be in a large instance to run all of this data in the cloud, you can accidentally click the wrong size instance, and that can often make things quite slow. So one thing that you can try if you're having trouble is to completely close the instance and then re-enter it and make sure that you get into a large one. What we're seeing, yes. So, I mean, in fact, even Eric, I now have confirmation from our technology guru that you accidentally have clicked an instance that is only 0.2 CPU and is not large enough to run what we're trying to do. So this is actually a very silly but useful learning example that even experts make mistakes, and that it's extremely important when you're launching to the instance to be aware of the size of what you're trying to do. And we know that EMIT is a big data set. And so to work with it in the cloud and for everything to be nimble and work nicely, it needs to be you need to be in a large instance, and that's exceptionally important. If you choose right here, right where Eric is right now, oops, well, if you choose the smallest version, it will not go well. And that's kind of what we've seen. And so that's an important thing to remember. And it's just an accident. Sometimes it just happens by accident, like here. So yeah, just please be aware of that. Hopefully we'll have a little bit less trouble moving forward. If you're still having trouble, please head over to the breakout session, and Aaron will walk you through the process of making sure you completely close down your instance and close that down and then start it up with the correct size. So yeah, thank you so much for your patience, and I'm sorry for this interruption, but it actually is a very excellent example of how with these new technologies, you just have to be a little bit careful, even when you do it all the time, of just getting into the right size. So hopefully, fingers crossed, Eric, these problems should be resolved for you now. And if anyone else still has trouble, please head to the breakout, to the technical help room. Okay, guys, one more interruption on my end of a technological update. Eric previously did not choose the wrong server. What had happened is when we set up the servers, there was a very small but important misplacement of a decimal point. So when you were choosing a large server with 16 CPUs, it actually was giving you a 1.6 CPUs. So I'm sorry about the kind of interruptions and the updates, but I've been just trying to get to the bottom of this on the fly, and I'm pretty confident that that's exactly what the problem is, and it has been resolved. So for those of you that are having trouble, this is the same fix. Like, just go ahead, restart the instance, and now when you correctly choose your large instance, it will actually provide you the number that you clicked on instead of 1/10 of that number. And that will be what you need to move forward successfully.
Okay, yeah, so if we can just go back and we'll all redeploy the instance. I think that'll fix everything if I understand correctly. So if everybody can just click this link here after they've shut this down. So you can go here and stop your server and then just close that window. And then if you click that link I put in the chat, it'll let you relaunch. And so relaunching should fix the issue that we were having. And then you should be able to open the notebook. So it'll put you in this EMIT data resources folder. You can go to how-tos, and we'll go ahead and do this extract area notebook. So you can just double click that and open that. And so what this notebook is going to do, let's say we have like a region of interest, and we only are interested in that information. We're going to be able to pull that out of an EMIT granule. So we just have this smaller subset of data. And so this will work like if you have like a shapefile or like a GeoJSON. So sort of our first step here within this notebook, as with the others, we'll just import our packages, and then we'll set our file path. And I think I've mentioned this before, but for this example, like we've got a shared folder where this EMIT granule is located that we're referencing. And so like normally you could just replace this with like the location of a file you've downloaded. And so we'll set that, and then we'll again use this emit xarray function. And what that does is read the data in to an xarray data set, and then it formats it in a way that it can be used by the xarray library and some other libraries to perform operations. And so it puts it in this format where we have our, and also it ortho-rectifies it. So we went ahead and did that step here, and that ran pretty quickly. So I think this is probably working. And so that'll ortho-rectify it, and so we can tell we've got our latitude, longitude, and band dimensions. Then we've got our full width, half max, wavelength parameters from the emit file, and also our spatial reference. And then our data variable is just the reflectance. And so now to subset that, what we can do is we can open a shape. Here we'll use GeoPandas to read this. In the data folder here, we've got this GeoJSON shape that's just a single polygon. So we'll open that. That'll give us our polygon. And if we want to visualize where that is, we can go ahead and plot it. And so I'm just going to use HV plot to do that. And first, I'm just going to select band 63 as a single band, just to plot this on with these specifications. And then we can also use HV plot to plot the shape file, or excuse me, the polygon that we've opened here. And we can see where that lays over this emit granule. And then simply to crop this, we could just use the clip function from Rasterio. We just need to specify the geometry part of this object, and then also the CRS. And I guess that's one thing I should have mentioned. Make sure your shapefile's in the right CRS for this. And so the emit data is just in WGS84, like lat long. And so is this polygon that we've read in. And then for clip, we'll use this all touched equals true parameter, which is basically going to include any pixels that intersect with the line that bounds this polygon. So if we run that, it'll go ahead and clip this data set. You can see it dropped it down to the latitude and longitude grid down to 140 by 163. So like a much smaller data set, but you've still got all of your bands there. And then we can just go ahead and plot that just to sort of visualize the smaller region that we've subset. And if you want, you can save this as a new file. And the format, we've got this in here. When you read it back in, you can simply just do a XR or Xarray open data set to reopen it and get back to where you were working from. Are there any questions on that?
Yeah, there's a question about why are you importing from OSGeo import GDAL in all the notebooks? It doesn't look like that package is ever used in the tools, and or aren't there multiple incompatibilities between OSGeo and Rasterio?
Actually, I think you can take that out. That's something I did not do a good job cleaning up as I kept modifying these notebooks. I believe that that is used by this emit xarray function, but that's in those, that's in that module. So I don't think it's necessary to have that as an import here.
Great. And then related, outside of this workspace, what's the best way to access the emit xarray function?
I'm sorry, can you repeat that?
Yeah, absolutely. Sorry, outside of this workspace, what is the best way to access the emit X-array function?
So that function, it's on in the GitHub repository. And so it's in this modules folder here. There's this emit tools.py script, and it has a bunch of different functions that you can use with the emit data. Like it's got this emit X-array function that basically opens and puts it in an X-array. And then it's also got some functions to do the ortho rectification and some functions to work with the quality information as well that Phil will present on in a little bit.
Great. There's a question about the extract to points notebook. Real quick, sorry, I should have seen this before. Which is what is the category field?
So the category field in this notebook, it's just an arbitrary category that I added as an example of like if you were doing a classification or something and you had some categories. I just wanted to illustrate like how you could pull that through during this process. These are actually just arbitrary. They don't mean anything.
Great. And then the last question that is live right now is, will this recording be posted somewhere? And yes, it will be posted on the EMIT website once we get it approved for release. So, so yeah, that's all the questions I've got in the Mentimeter. So back to you.
All right. So if there are no more questions, I guess we can move on. I think next, Phil is going to talk about the quality layers and masking. Is that right?
Sure, that sounds good. I can, let's see, share and get that going here. Hopefully everyone's seeing that. So we're navigating over to this how to use a emit quality data tutorial next up in this notebook. And I should note that Eric is really the author here, and that I'm mostly presenting this on his behalf. Again, this is the kind of comments about the Earth data login and kind of where the setup instructions are similar to before. We're going to go through a little bit more details about the L2A mask file that many users might want to be interested in, and to try to break that down a little bit more than before. So let's see. I'll just go ahead and do some imports here, and then we'll load up a scene. I'm going to load up a slightly different scene, just that's a little bit more illustrative for the purposes of cloud masking. So the first thing that we want to do is read out the sensor band parameters, which in this case are going to tell us what the mask bands are. So we can look in the sensor band parameters group, and then we can look in the mask bands location, and that will tell us what the name of each one of these mask bands is. So we have a cloud flag, a cirrus flag, a water flag, a spacecraft flag. Then we have a dilated cloud flag, and this dilated cloud flag is a radius around the joint cloud and cirrus flags using an assumed cloud height of, I believe, 4 kilometers, as well as the solar geometry in order to construct a radius buffer around that area. So that dilated cloud flag is basically cloud, cirrus, plus some buffer. And then in this file, we have 2 non-flag components, and that's the aerosol optical depth at 550 nanometers. And this is a product of our level 2A reflectance retrieval process through the atmospheric correction, as well as the water vapor in grams per centimeter squared. Now, both of these are not used directly as a mask, but certain users in certain situations may want to utilize them in that way. For instance, if you are trying to look at particular mineral absorptions that are only very obvious, that are very close to the dominant deep water absorption features, and you want to make sure that you have a limited amount of water in the atmosphere, you could use a threshold on the H2O, or similarly, if you were focused on near IR features or particularly visible features, you could look at using particular cutoffs at the AOD flag. And for our mineral retrievals, we in fact impose a threshold of, I believe, 0.4 for AOD in those. And then there's an aggregate flag that is basically all of these flags plus that AOD flag that I just mentioned coupled into this aggregate flag 7. And that's what the downstream products from the official EMIT repositories will use as their masking for generating the L3 products, but individual users might choose to use different ones of these for different instances. So let's take a look at what these different flags actually are on an example set. So this is just a quick set of code that I probably shouldn't have run. Nope, it's going, that's okay. To just display the RGB and then the different flags sitting next to it. There, okay. And so you'll see in this scene that we've got kind of some scattered clouds on the top. Now, our cloud detection algorithm is still undergoing some revisions, so right now it's a pretty simple version of things, and it's still fairly conservative. So there's a decent number of clouds that aren't getting flagged that you'll see here over to the right. So it's getting some of them, not all of them, particularly in the denser patches. We'll have an update for this by the time that we reprocess the data to the DAAC. So here's this cloud flag, and then here's what that dilation looks like over to the right. In this particular scene, there was nothing flagged as cirrus. There was some AOD and water vapor. I'm going to come back to those in just a second in a little bit of a better view. There are a couple pixels of water scattered throughout the scenes. There's a little bit of standing water that comes through in our water flag. And then the spacecraft flag, perhaps unsurprisingly, is not showing up. This is mostly for when the solar panels on the ISS are in a particular configuration that we might end up seeing them around the edges. So we flag them here in a different way. And then here's this kind of aggregate flag that you can use down below. If we step forward, I just want to call out these AOD and water vapor bands in particular with a little bit of a different stretch. So here's the AOD from 0 to 0.6 as we retrieve it. And I will note that for some users, this might be your signal, right? There are some atmospheric scientists out there that might be interested in either the AOD or the water vapor retrieved. So you can come here and you can get that as a signal, or of course you could use this as a threshold. So this particular scene that we're looking at is a relatively challenging one. It's above 3 grams per centimeter squared of water vapor. You can see that the retrievals tend to fail in the middle of that cloud. But so this is a pretty tough one in terms of the overall atmospheric correction. We might see that down below. All right, so here's that mask key again. So I'm going to switch forward from looking at the masks to trying to apply them to the data. This is pretty straightforward. Eric put together a nice EMIT tools quality mask flag, where basically you can specify which flags you'd like to use, and it will just aggregate that together in a quick mask for you. So in this case, we can go ahead and choose to use 0, 1, 2, and 3. We can combine that into our mask. And then we can go ahead and deploy that and end up seeing what a masked version of that looks like. So here's again that RGB, here's that maxed out area. Looks like I forgot to actually mask out what those RGB values were, but we could do that. Here, I will do it on the fly to demonstrate what this can look like. So here's an RGB copy. And then we can just say, we can bring that right in. So that should be able to mask the RGB data out on the fly, except that I did something incorrectly there, which is why you don't make edits to your tutorial live when you're doing a demo. So rather than debug in front of everyone, I'm just going to bring this back to what we had before and show that spectrum there. And see that as is here. And then I'll note that you can use the QMask parameter into the xarray function, and you can bring that right in the converted xarray, which you could then plot out. And so in this case, we're going to bring that in and then also orthorectify it. So this will show us what the actual masked out version is. If we come down here and just show the red band at 650 nanometers, you should see that projected out onto a map.
While you're waiting for that map to come up, what kernel did you use for the dilation operation?
So it's not actually a kernel based. So it's a distance based with a ray trace. So it's basically using the combination of the solar geometry and an assumed cloud height at each location to infer what the maximum distance away that something can go. And the main rationale for that is that it's trying to encapsulate where cloud shadows might be, so the entire cloud field based on that ray. Now that's a fairly conservative estimate because of course it's in that's only in the cloud shadow direction. There's another direction that's probably shadow free, but for the kind of the downstream purposes of the EMIT products, it's sufficient. Eric, I'm not sure, maybe I did something funny here so that this isn't showing up, but I probably broke this a little bit earlier and I apologize for that, but we'll get this updated.
You're running at 35 gigabytes in memory. You might want to restart your kernel.
Okay. That's probably why. So I'm going to refrain from doing that on the fly live here, but and I'll just move forward. But in general, this will give you a for those of you out there that can run it, this will give you a view of the red image that's just had that cloud mask applied to it directly with those data masked out. Maybe I'll pause here and take any other questions before we get to the band mask data.
I think the other question may have come in kind of right at the end of Eric's session. It's asking if I want all pixels contained within and intersecting with but not touching my area, would I set all touched to false?
Yeah, I think that's going to do exactly what you're looking for.
Great, thank you.
Great. Then I'm going to move forward a little bit to talk about the EMIT band mask data. I'm curious, I can't see the participants list at the moment. Is David Thompson in the room?
Hello.
Hey, David. I'm going to talk through some visualizations of the band mask here in a second, but I don't know if you want to just say very quickly a little bit about what the band masking is doing and what its purpose is.
Sure. And this goes back to kind of the guts of the instrument and how we produce calibrated radiance data. With any focal plane array, and that's of course the light sensitive element at the heart of the spectrometer, there are a certain number of elements that are inoperable, that is, that don't respond to light. And so we have to do something with those values to avoid holes in our data cubes. And so the strategy that we use with EMIT, which has also been used over a decade now for airborne instruments, is to do a data-driven interpolation. You can't just interpolate, you can't just draw a line over the hole because of things like sharp atmospheric features that would be disrupted. It would put all sorts of artifacts in the data. So we use a statistical interpolation strategy to impute the most probable value for all of those missing data points, and of which there are only maybe like a few dozen across the focal plane array. That is a few dozen individual data values within spectra. but we don't want anybody hanging their critical, cover of science result on a data value that's been imputed. So we supply this band mask as a way of telling you which data were measured physically by the instrument and which data points were sort of intelligently interpolated. There's one other reason that a data point could be interpolated, and that's if the detector itself is saturated. So we have a limited capacity to accept photons as EMIT flies over the surface of the Earth. And if we are overflying a really bright target, maybe snow or a really bright playa, clouds often, you can actually saturate. This doesn't affect any of the other spectral channels that aren't saturated, but over some region of the spectrum, there'll be a number of channels that aren't usable. So those count as bad data values too. And we will identify the most probable value for those spectra. So it will look cosmetically okay. But again, you'll want to, particularly if you're doing snow studies, you might want to check the bad data mask just to make sure, what quantity of the data points in your maps are actually interpolated versus real measured spectra. Is that what you had in mind, Phil?
Absolutely. And don't go far. I have some snapshots of the focal plane array that you can walk through in just a second here. So the way that these data are stored in what's named a band mask, a band mask, not bad mask, a band mask value in the mask net CDF. It's really, like David's saying, not so much a mask, but as an indication of where that interpolation has occurred. Now, it's stored in a little bit of a tricky form, which is a 36 element packed unsigned integer array. And so you'll need to unpack that. So basically what that means is that you get multiple values per each one of those unsigned integers. So you'll need to unpack that in order to view each one of those components, which you can do with this band mask function that Eric's put together under the EMIT tools. So you just run this guy, and then you end up with a band mask, and you can see that now its shape is the down track dimension, the cross track dimension, and then the number of wavelengths. And so here, the first thing that we're just visualizing is if you take a look at the very first down track component. So this is basically a view of the focal plane array. It's transposed, but it's effectively that. Now you can see what the cross-track element location is, and you can see the wavelength element location. So David, I think this speaks pretty directly to the view that you were just trying to cast. Is that correct?
Yeah, that's right. So this is exactly what you would see if you were looking directly at the focal plane array of the instrument. And there's some number of bright pixels there in that image, which are interpolated values. And this could be due to, for example, saturation in that spatial location around 200 pixel 250 there.
Yeah, exactly. And I think in this instance, that's a cloud. So that's what's causing that. Then I'll just bring to the note that you can view that into the spatial domain as well. So here's just plotting, for example, the 234th band. Now in the down track direction, you're going to see that particular wavelength always have that mask in, because this basically was that particular wavelength at that particular position of the focal plane array. So this kind of exaggerates the view of what that effect is in the downtrack position, but you can view the data this way as well. So hopefully that wasn't over the top and gives some insight into what this can be utilized for. Again, particularly if you are using, if you're looking at areas that are prone to saturation, this is a good data set to just double check. Maybe I'll stop there and ask if there are any questions, and then we can move to our next topic.
Yeah, there's one question here. about, could you say more about saturation over snow and its prevalence? Is this occurring on most sunlit slopes during the spring when the sun is high, or on various slopes in the winter when the sun is low, or just a few pixels here and there? David, do you want to just speak verbally to that real quick?
Sure. And there are many snowfields that don't contain any saturated data at all. It starts to happen more under when the sun is very high in the sky, as Carl was suggesting, and particularly if you're in an unfavorable scattering direction, then you can get sort of the directional scattering effects of snow can cause large reflections in certain directions. So that can also cause saturation, but it's sporadic.
Great, thanks. And I think that's it for the questions for now.
Cool. Then I think help me guys remember. I think our next topic is on the spatial components and Git. Is that what we were? Is that next?
Yeah, we were just going to have a brief discussion of kind of geotransformation and resampling considerations for spectral data as people reproject. And
great. Then I'm going to go backwards in slides. I think I did things out of order, but that's okay. All right. So I think the purpose here was kind of to answer some questions that we've been getting asked a lot, and so we kind of just wanted to convey how we're thinking about the process. Of course, different folks think about this process differently, and so we've tried to give all of the information so that everyone can do what they like with the data. But we just kind of wanted to lay out how we think about things and what our kind of general workflow is when we're doing these kind of spectroscopic analyses. So the first is a question that we get a lot is kind of why are the data provided without a projection? And then when we do resample or orthorectify things, why do we utilize a nearest neighbor resampling strategy as opposed to bilinear or something like this? And so this kind of gets is an attempted visual explanation of why we try to keep things into a nearest neighbor interpolation scheme and why we do things kind of in the unprojected format. So if this, bear with me here, this is a difficult visualization to go through, but if we assume that this is some truth on the ground and that the world is full of only these red, blue, and yellow squares, then and this is just how the world was, and we had a sensor that passed overhead, we might observe it in something that looks like this. So say our observation block were these 16 by 16 blocks. If we did that, then you would basically blend up in a perfect linear mixing regime. You would blend up all of the components that are in each one of these, and you would observe whatever that blend happens to be. So if you happen to be aligned with these grids, all's well, and that's your observation. Now, of course, if you end up looking at the truth of what that mixed pixel is, then down below, so say we look at this center grid block here, which is the mix of this red and blue, of these red and blue tiles. The truth of that center mixed is this purple, right? But depending on how we did an interpolation scheme, we might end up with something during that interpolation that is a totally new color on top of that, right? And I think that this is just showing what the effect of that spatial mismatch can be, but you can have both a spatial and a spectral effect that come into play here. And basically make the pixel that's being observed a fundamentally new pixel, which is something that we don't want to do. So to get around that, our suggested workflow is and the way that we provide the data is to is to keep everything in its raw format and preserve any and all subtle signatures that might be there, and then give all the spatial information so that you can do a quick orthorectification after you've done any geophysical interpretation. And so just to drive that home, the way that the EMIT SDS workflow works is that we start with reflectance or radiance or reflectance uncertainty, right? Any of these products that we're going to look at in the native geometry of the sensor without any orthorectification applied. We execute some sort of retrieval code. So for example, our level 2B mineralogical procedure uses tetraquarter in order to retrieve the minerals at the surface. And then we utilize the built-in GLT table in order to orthorectify that product. So before in these tutorials, we've generally been projecting these reflectance data. As you've seen with these, with the computational challenges that we've had today, it takes a lot of memory to do so, right? This is an intensive task. And so by waiting until we've done that retrieval and then applying the GLT, we keep things relatively low in memory during that shift, because the application of the GLT introduces a lot of additional no data values kind of around the edges. And then lastly, you can write that output into a compressed and probably tiled format for whatever kind of application you're looking at. Now, you could write it out into an ENVI format. You could write it into a cloud-optimized geotiff. You could write it back out into a netCDF. You could pick whichever format you like, but this kind of gets us there. So that was probably not the clearest explanation in the world. I apologize, but hopefully it gives a little bit of insight into kind of why we're providing things in the spatial domain and kind of what our suggested workflow is and how we think about moving things forward, at least in bulk on the EMIT science data system. Dana, if there are questions, I can take them there. Otherwise, I can do a little bit of a topic on Git here.
Yeah, there's a quick question here. Any thoughts about using a raster format that can store multiple samples within a pixel, like deep EXR?
That is a very interesting notion, and I don't think that we have considered it yet. So that's a great comment. I think we'll have to think about that a little bit more.
Great. And then there's a question about the kind of data flags, where do the flags discriminate between smoke plumes and clouds?
So I haven't looked practically thoroughly through our data sets yet, but in general, the purpose of the cloud mask, yes, is to flag these individual clouds, whereas the AOD, the aerosol optical depth, is intended to identify the smoke plumes. And I suspect that is likely the way that those two masks are going to work. And then we apply a threshold on the AOD in order to filter out cases where the AOD values go high. I suspect those are not being caught by our cloud mask, but I would actually have to go through the data and confirm that in some smoky and cloudy adjacent areas. It's possible they get caught by both.
Great, thanks. Bree has her hand up.
Could you bring up that image, that slide you were showing before, Phil? I just had a kind of clarifying question. I guess it's like very tidy here in this cartoon. And so I was just wondering, like, could you say a little bit more about how this works, like in real life? Like, are you always looking at the centroids, or is it like a common moving window in which things are being like understood as truth? I just was looking for a little bit more detail on how this might work like in real data.
Sure. So I guess I would say that at the limit, real data might end up looking something like this, right? Like in a perfectly flat surface, and when you zoom in small enough, you can think about this as being a combination of individual small reflectances. And I know that there are nonlinear mixing regimes and reasons that this analogy breaks down quickly, so it's not the best. But effectively, each location on the ground is observed by the instrument, right, and by each detector element at its particular position, and you end up with a what's not actually a square grid, right? Right, a pixel is a little bit of an artificial notion to call that a square grid on the ground. But we're approximating that on the square grid on the ground and thinking about that in that way for now. And within a particular location, say there is a location that has some sort of subtle signature in a location that's right here. That's let's say it's in this particular pixel, and say there's a
So like something like methane maybe, or
let's
something
say
like,
there's a methane absorption feature right here,
okay.
right? If that signature is going to be very subtle, and so you're going to want to not mix this pixel together with this pixel before you do your spectroscopic analyses, because if you do that, you're going to blur that feature a little bit and make it harder to detect. So by keeping everything in its kind of original frame, have the maximum amount of information as the sensor solid available, you can make your analysis to the best of your ability, and then you can apply whatever kind of projection you're looking at. And maybe I'll invite, I think Rob is on here as well, and Rob might have some additional thoughts to throw in here.
So again, it's a pleasure to be here. I put a paper in there that I got from Phil Townsend, which is written by another team, which tries to make this point. With spectroscopy, we're in a new world where the great power for the application is often revealed in very subtle signatures: methane, nitrogen in plants, subtle lithium-related signatures in rocks, the coastal ocean, phytoplankton, benthic signatures through water, coral. And everything we've been learning is that resampling tends to wash out those signatures. So you want to get the information and then resample, with the weighted resampling to orthorectify. And I Phil said that beautifully. And then the other thing that Phil is hitting there is that you can, by weighted resampling, you can create signatures that weren't really present because you've taken a little bit of something that wasn't in one spectrum and put it in another spectrum. So those are the two reasons with imaging spectroscopy, our workflow for EMIT and our recommendation with what we understand right now is to resample at the end after you've got your products. And we're doing everything we can to make that as easy as possible, the GLTs. We really want to make this easy as well. So we want to learn and listen, but that's sort of our thinking right now with the evidence that we have seen. And I'll leave it at that. I put the reference to that paper that Phil Townsend pointed me at, which is making a similar point. Thank you.
Thanks, Rob. Dana, should we move forward to doing a little bit of a Git tutorial here?
Yeah, absolutely. I think we're all caught up in questions. So thanks, guys.
Okay. So in a next little section here, we've had a lot of questions about how you might be able to interact or contribute to some of these wonderful tutorials that Eric and team have put up. Say you have a new suggestion of a tutorial that you think you've put together some code and you think you'd like to share that with the community. I think we welcome that, and we wanted to just touch base on a little bit on how you can do that. And so many of you are probably pro GitHub and Git users, so bear with me. But we're just going to do a real fast walkthrough here, and then I'm going to do it in slides first, and then I'll show you on the command line real fast as well. So, right. So what are Git and GitHub? So the first thing to recognize is that Git and GitHub are different things. Git is a version control software system that makes it easy for you to have multiple separate development flows going on the same set of code, and to interact with colleagues through a formal mechanism that tracks your changes and facilitates merging in a relatively safe way. GitHub is a web portal that hosts individual Git repositories and that you can push and pull to and share things from dynamically online. So think of GitHub as a source of where Git repositories can live. How do you interface with those? So most people here, I think, have GitHub accounts because that's what you've provided in order to get onto these notebook instances. And anyone who has a GitHub account can fork a repository. And when you fork a repository on GitHub, what that means is you are making a clone or a copy of that repository that you own. So that fork is now on your repository. You own it, and you can make modifications to it. So once you make that fork, you can then, that lives on your GitHub account, and you can then push and pull from that, so you can make a copy of it locally or on any other server that you want, and you can make any changes that you might want to there. And then you can recommit those changes back and forth onto GitHub. And if you think that it's something that other folks might want as well, you can issue a pull request that will ultimately be reviewed by the repository maintainers. And so if the repository maintainers think that that's a contribution that'll help everyone, they can merge it right on in. Let me show you that workflow here to drive that home a little bit more clearly. So I'm going to go over to a repository here, the EMIT SDS L2A repository. And you can see up top here is this fork. So it tells me that I can fork my own copy of this. So I'm going to go ahead and hit that button. And what it's going to say is that it's going to make a copy for me under my username. And I'm going to say, yes, do that, create that fork. Okay. Now this automatically redirects me, and now I'm looking at my fork of my repository here to the EMIT SDS L2A. So if I go over and look at the code, I can grab this tag here that tells me what the link to that repository is. And I'm even going to do this live in this instance. So if we go over back to this instance, one of the things that you can always do is you can make a new terminal, and you can actually just grab this terminal right here. I have one going right here, and I'm just going to go into a new directory that I'm going to call temp. And now I'm going to do a git clone from that location. Now, if you haven't done this yet, it's probably going to ask you to add some credentials, and you can make a SSH key. I'm not going to do that live just so that I'm not exposing my personal SSH keys here. But you can easily make one of those and add it to your account to authorize it. So here's that cloning of that repository. You can see that now there's this emit STSL2A notebook. And let's say I want to make a change to this make emit masks function. And so I'm just going to say this is a okay, so I will make a quick modification and save it. If I do a git status, it'll tell me that that's now been changed. I can add that component, and I can go ahead and say git commit, add my new comments. So I have now made my changes. I have added my changes to my local repository, and I've now committed them. So they're now saved in my local Git account. To push that back to the main repository, I can check what my remote name is, and I can git push to origin. That's the repository that I want to push things to. And I think I'm just pushing to main here. So I'm actually going to create a branch first. Sorry, making a new branch there. And these changes are on this new branch because I've already committed them, which I can check by typing git log to check my previous comments. And now I can push those changes. I can push my new branch to the origin. And a lot of this is documented very well online, so I'm just moving through it very quickly here. But when I push this new branch online, now if I go back to my repository, you can see that new branch has been pushed up on the GitHub. And this is where I would come and say, ooh, I want to merge this back in, and so I can compare and pull request. This is where I'm asking the developers to review this branch and see if they'll accept it. And I can type them a comment and I can say, hey, should probably actually delete this. Now, normally I wouldn't actually go ahead and hit that pull request, but since I'm one of the maintainers on this STSL2A repository, I can go ahead and clean that up later. So we can go ahead and quickly create that pull request, and it will check for auto merging, and it's now staged up there. And you can see over here what files were changed, and if the repository maintainers accept it, it'll get merged right into the main repository. All right, that was a lightning fast version of how does Git work and the suggested workflow. But the thing I think that we really want to encourage everyone to do, and there are, again, many resources about Git and GitHub online, we really want to encourage folks to use the go ahead and pull your repository down, or go ahead and fork the repository first, clone that repository, make any changes that you might want to do, push it back up to your repository, and then issue a pull request to suggest those changes for the collective group. Does anyone have any questions there?
I'm not seeing any questions in the Mentimeter on this particular topic. And I think that brings us to basically the end of our planned topics. So we could go ahead and have, and I don't have a backlog of questions this week. So I'd be happy to take any additional questions right now. And I know that, we have this time set aside, so we can also turn off the recording if we'd like to take some time to answer some more individualized questions that are maybe specific to research projects or other things. Bree.
I'm pretty interested in using EMIT data in the future. Are there any opportunities coming up, or is this community going to be, or things coming up in the future that we can look out for, or a way to stay connected to what we have going on now?
Thank you so much for that leading question and reminder at the same time. Yes, there are those things. We are, so the recordings for this will be available. We are continuing to be active on the Slack channel to answer questions that you might have. If you haven't signed up for our kind of Slack channel and or mailing list, that will be a way that we're communicating with folks. We anticipate that there will be a call coming out for proposals around EMIT data soon. We don't know exactly what that will look like, but when that is announced, we're hoping to have a community webinar to kind of give folks some information about what the status of EMIT and EMIT data and EMIT science is at that point. So you'll be receiving information about that if you are on one of our communications lists. And I will be sending out a follow-up email, thank you and follow-up to everyone once all the recordings are posted. The first one has been put up, and the second one hopefully will be up early next week. And then, you know, as soon as we can get the last one up, that'll be a full set for y'all. Yeah, I think that's those are the main things. And I know that, you know, with our colleagues at the LP DAAC, we have plans and hopes for continuing to do workshops that we will keep you informed about. But I don't want to make any specific promises yet. All right. Thanks, everybody. I will go ahead and turn off the recording now, and we can kind of keep this open as office hours until noon if people are interested. So thanks so much.